Hi everyone. This next lesson is going to be on forces. This is the next topic along and the final topic in mechanics. So we'll be looking at forces and talking a little bit about vectors as well. The main focus for this lesson is about Newton's laws, and we're mainly going to focus on Newton's second law and talking about resultant forces. So this is what we're going to cover. We'll go over Newton's laws. We'll talk about what a resultant force is and how we find out how we calculate it. We'll talk about forces as vectors and how we can use vectors. We'll talk specifically about Newton's second law because that's the one we use most commonly. And we'll finish off with a practice question at the end. It's really good to go over this lesson before the next one on pulley problems because a lot of that and a lot of the setup for the pulley problems questions make use of Newton's second law. So if you've got a really good handle on this, it'll make it a lot easier to master that next lesson. So let's have a look at Newton's laws first. There's three of them, Newton's laws of motion. The first one is an object will remain in its current velocity if no resultant force acts on it. So it's easy to think that we need a force to keep something moving, or we need a resultant force to keep something moving. It's not actually true. If you're in space, you don't need a force to keep moving in the direction you're going. It will just maintain its current velocity if there's no force acting on it. The reason we tend to think that on Earth is mainly because of friction. Friction slows us down, so there is actually a force acting on us, slowing us down. But in general, if no resultant force acts, an object will remain at the velocity it currently has. If the object is stationary, it'll stay stationary, okay? It'll stay at zero velocity, if you like. Newton's second law, which is the one we're going to focus on, is about acceleration and force. It says the acceleration of an object is proportional to the resultant force acting on it. And in fact, we can write an equation for that, which is that F equals ma, probably the most important equation in mechanics. So make sure you remember that one. We'll be using it a lot in both this lesson and the next lesson. Probably the most famous law, but quite a difficult one to apply, is that for every action there's an equal and opposite reaction. This is quite a difficult one to describe, and it's quite often misinterpreted. But it's kind of like looking at a force interaction from two different perspectives. When you stand on the floor, you feel a force from the floor pushing upwards on you. But if you imagine you're the floor for a second, you feel a force pushing down on you, okay, on the floor, okay, and it's equal and opposite when you look at those two different sides of the force. It's basically the same force viewed in two different perspectives, and those are equal and opposite, so they point in different directions, but they have the same size, the same magnitude. We're not going to talk too much more about Newton's third law. We're going to focus on the second law. So what's the resultant force? This is really important to be able to use Newton's second law and the first law. The resultant force is the overall force acting on an object. So I've got a quick example here to show you what I mean by overall force. If we've got a car and there's two forces acting on it. This one could be from the engine, providing a 2,500 newtons even force forwards. And let's say we've got a 1,750 Newton force backwards. That's probably due to air resistance mainly, and also partially due to rolling resistance. Okay. Rolling resistance is the resistance from the tires. Okay. Now, if we've got 2,500 forward and 1,750 backwards, the resultant force has to combine both of those. We take the 2,500 forwards and subtract the negative force away to leave us with an overall resultant force of 750 newtons. So the overall force points forwards, because this force is bigger than the backwards force, of 750 newtons. Okay, so that's how we figure out the resultant force, the overall force on this car. Let's have a look at another example. This time we've got a crane picking up a wrecking ball or whatever it is. It's got a mass of 500 kilograms. Its weight is acting downwards towards the earth. And how do we work out what the weight is? Well, hopefully you remember this equation here from the very start of mechanics when we talked about weight and mass and gravitational acceleration. It's W equals mg, and that gives us a way to work out the weight if we know the mass. Remember that g is 9.8 on Earth. Okay, so I'm going to use that value here. That's normally given to us on the exam paper. And to do that, I can do 500 times 9.8, and that gives me a weight of 4,900 newtons. Remember that weight is a force. Okay, don't forget weight is just a force, so it's measured in newtons, whereas mass is measured in kilograms. So that weight is going to be 4,900 newtons, and we're saying there's a force opposing that, which is the tension in the cable, and that pulls upwards to stop the wrecking ball crashing towards the ground. If we've got a 5,000 Newton force upwards and a weight of 4,900 newtons downwards, to figure out the resultant force, we just subtract one from the other, and we're left with 100 newtons resultant force. The resultant force is 100 newtons upwards. I know it's upwards because the 5,000 Newton force upwards is bigger than the 4,900 Newton force downwards, so it must be actually the upwards force that wins.